Hi, so this is lecture 16, Introduction to RF. So we covered a lot of this material the other day in lecture, but we didn't quite finish up this lecture, so I thought I might as well go ahead and just record the entire lecture here so that you have it all. Okay, so I'll go a little bit faster through the first part of the slides, since we've already covered this material. The number one thing that we do with RF pulses, the number one thing that we do with selective RF pulses, is we excite slices. Right? So this is what we do in MRI. In NMR, you don't necessarily excite any slices. You just need the RF pulses for excitation and refocusing. So that's why I make that distinction. Now the basics of slice selection, I'm going to talk about next. So let's see. So we put the object in the body, or we put the body into the scanner, and it polarizes. Right? That is, all the protons align with the main magnetic field. And so the main magnetic field we denote mathematically as having the strength B0, which is usually quoted in Tesla, and the frequency at which protons precess around that main magnetic field is equal to gamma times B0, where gamma is the gyromagnetic ratio. Equivalently, the frequency in hertz that spins will resonate at is gamma by 2 pi times B0. And gamma here, I'm going to zoom in so I can write this out more clearly. Gamma is given by 2 pi times 42.57 megahertz per Tesla. Okay? Okay. So, let's see. So we put the object into the scanner, and then we want to select only a limited region of the body to image, right? We usually don't care about imaging the entire body. We want to just image some subsection of the body. So we use the RF coils combined with the gradients to do that. So let's say we want to excite only this slice here. And so what we'll do is we'll use an RF coil that emits an RF field that is primarily what we care about is the magnetic field that's emitted by this coil. Right, it emits an RF field, and we play it out simultaneously with the gradient. So we're going to turn both of these on at the same time. And what the gradient does, this is the gradient field. It's the gradient field. And what the gradient does is it's going to create a frequency distribution given by omega equals gamma times G times Z, where Z is the spatial location in meters or centimeters is usually what it's quoted in. And so what we do here is we turn on the gradient at the same time as the RF is emitting waves into the body. And if we play out in the RF coil a band-limited pulse, then only the magnetization with precession frequencies that are inside the range of the bandwidth of the pulse are going to be excited. Okay? So the key thing here is that the gradient field maps space to frequency, which allows us to play out a pulse containing certain frequencies and it will only affect a certain region of space. Okay, so to show that graphically, again another way, we say that the gradient creates this linear relationship between space and frequency. The slope of that line is gamma times G, right? And So if we play out an RF pulse with the following spectrum that has a rect kind of shape, then we'll get a slice profile that is also a rect shape. That is only magnetization within the same bandwidth as the protons that have the frequencies of the RF pulse will be excited significantly. The rest will be left pointing along B0. So this slice profile is really plotting the magnitude of the transverse magnetization component, and you'll see that again in a little bit. Okay, so then to get a slice profile like this, like a rect function, we would want to play out the Fourier transform of a rect, which is a sinc. In practice, we can't play out infinitely long sincs, so we have to truncate them, which has effects that we'll talk about in a little bit. So the Fourier transform then of the RF pulse, which we call B1 of t, is this guy, which is like a rect function. It's ideally a perfect rect function. Let's see. And I should say that this relationship, this Fourier transform relationship, is the most accurate at low tip angles. And again, we'll see that mathematically in a little bit. So in addition to slices, we have other geometries that we can excite. We can excite just a thicker slice, which is a slab, but fundamentally this has a different use than a slice selection, because when you excite that thick of a slab, you're also going to be doing gradient encoding along the z dimension, along the slice dimension. That is, you're going to be doing gradient field encoding along this dimension, so you're going to end up with a 3D image, whereas when you do slice selection, you usually don't do encoding along z. There's also a cylinder excitation. You can create that using a spiral pulse, and that's often used for navigators. And then you can do voxels as well, and that would be used for spectroscopy. Okay, and there are three different types of excitation operations that we're going to be doing here. We have excitation, inversion, and spin echo pulses, and each does a different thing to magnetization. Right? So the excitation pulse is going to take magnetization that is initially along the z-axis here, and it's going to rotate it down to the transverse plane. So in the example I'm going to draw here, we're going to rotate it from z, so the magnetization M0 is initially pointing along z, and then it gets rotated down to the transverse plane, and it would rotate down to the y-axis if you had B1 pointing along the x-axis. So the rotation happens down here, and this is the magnetization after the pulse. And an inversion pulse is going to also operate on magnetization that is initially pointing along the z-axis, but it's going to invert it down to the negative z-axis. So in this case, I guess it doesn't matter which direction the RF is pointing, but if it was pointing along x, it would rotate down to the negative z-axis. It's going to basically negate the sign of the mz component of the magnetization. And a spin echo pulse, though, is a little different, and it's going to rotate magnetization that is already in the transverse plane by 180 degrees back into the transverse plane, right? And so if the RF is pointing along this direction, then it's going to take, and the magnetization is initially sitting along y, it's going to rotate that magnetization to negative y. And so we do this in order to refocus phase dispersion due to off resonance. Okay, so to give this RF stuff a little context, we have three magnetic field sizes in MRI that have the three fields have very dramatic different magnitudes, right? So the B0 field is by far the biggest, and a typical B0 field is about 15,000 Gauss, but that's equal to 1.5 Tesla, right? And so that is the strength of the main magnetic field, and 1.5 Tesla is just a typical clinical MRI field strength for scanning humans. And the gradient field is the other one. That's usually represented just by the letter G, and that guy is linear in space, but typically the biggest gradient slope you can play out is 4 Gauss per centimeter, and then you might have a total field of view of 40 centimeters, so it'd be 20 and minus 20 on each side. So then the biggest magnitude of the gradient would be 4 Gauss per centimeter times 20 centimeters, and that is equal to 80 Gauss, and that would be peak then. In the center of the magnet, it again is 0 because it's a linear field. And then the B1 field is actually quite a bit smaller than that. It's usually about 1/4 Gauss, right? And Earth, it's actually even smaller than the Earth's magnetic field, because the Earth is about 1/2 Gauss, right? So the B1 field, the RF field that we're going to spend so much time playing with, is by far the smallest of these three fields. Now, one question is, if you see that the Earth's magnetic field is on the order of 1/2 Gauss, it's actually even bigger than the B1 field. Why isn't this a problem? Well, it's because the Earth's magnetic field is not on resonance. It's a DC field, while the RF field that we're playing in, we're creating an RF field that oscillates at the same frequency that the magnetization is resonant on. So the reason that the Earth's field is not a problem is that it's DC. It's constant in time. Okay. So there are then also we can look at the typical power requirements of these three fields. So the B0 field, once you ramp up a superconducting magnet, requires no additional power we don't have any amplifiers driving it directly at all. The gradient field, though, does require power, and it usually uses about 2 kilowatts per channel. And then the B1 field is about 20 kilowatts per channel. So it's a lot bigger. It's kind of funny. And sometimes we have multiple RF channels. It's kind of funny that the RF field is by far the smallest field that we have playing out in the scanner, yet it requires by far the most power, orders of magnitude more power than the other guys. So about 20 kilowatts is what you would see out of a body amplifier at 1.5 Tesla. That's the peak power output that you can get out of it. Okay, so where does all this power go? We're definitely not putting actual 20 kilowatts into the body, right? We'd be cooking the person. So if we look at where it's going, we can say that 20 kilowatts is the peak output of the amplifier. 2 kilowatts is really the average power at a 10% duty cycle. So meaning that the amplifier is on for about 10% of the time, so it's actually on average putting about 2 kilowatts out. Then you have a lot of cable losses, and about 200 watts actually gets dissipated in the subject. And then only about 20 watts of those 2 kilowatts average gets imparted to spins. Okay, so it's really not an efficient process. What are the physical effects of these different fields? We know that magnetic fields can have effects on the body. The B0 field, as long as you're not shaking your head around too much and inducing currents in your head from the motion, really has no known effect on the body. The gradient field has no effect so long as you're not oscillating the gradient field so fast that you induce nerve stimulation. And the B1 field, though, does heat up the body. And the FDA says that we can heat up the body between 1 and 3 degrees C. Okay? So you can imagine that there might be different limits on the amount of RF power that you can deposit in different parts of the body, because different parts of the body might be deemed more important than others. So in the head, you can, or more sensitive to temperature rises than the other. So in the head, you can deposit the least energy, and you can really only create 1 degree C temperature rise in any 1 gram of tissue. In the body, it's a bit higher. You can create 2 degrees C, and in the extremities, you can really go nuts, and you can go up to 3 degrees C for any 1 gram of tissue. And SAR is really a very, the RF power deposition is measured in terms of SAR. SAR stands for specific absorption rate. Okay, and it's a measure of the amount of power going into tissue, and it's a really very complicated relationship, because you really have to know what the electric fields are, you have to know what the tissue density is, and you have to know what the you also have to know what the conductivity and permittivity are of the body, the electric conductivity and permittivity are. And so, and at the same time, you start heating up the body, and the body actually changes itself a little bit, right? It might start increasing blood flow to the region that's getting heated up so as to remove heat. So it really depends on a lot of factors, and it's very difficult to predict accurately, but it depends on vascularization. These are some of the things that vascularization. It depends on conductivity. So that's an electrical property of tissue. And it also changes through the body. The two major different tissue types with very different conductivity in the body are water and fat. It depends on tissue geometry, right? How is the tissue, that slice of tissue in the body oriented with respect to the RF coil? It depends on the coil volume. And it depends on the pulse sequence you're playing out, just how big of RF pulses are you playing out, meaning how much power are you putting in. And accurately predicting SAR really requires complete knowledge of the electromagnetic environment in which you're creating the pulses. So that includes having to know what the coil configuration is. You have to know the body properties, and that includes conductivity, density, and permittivity. And you have to know the blood dynamics as well to really get an accurate hold on how much you're heating up the tissue. Roughly, though, if you ignore body dependence for the most part, which is actually okay at lower field strengths, you can say that SAR is proportional to B1 squared, the magnitude of the RF field squared, times B0 squared, and you get the increase with B0 squared because the electric field, by Maxwell's equations, is dependent on the time derivative of the magnetic field, right? And the magnetic field is increasing in frequency as omega. And so then we also get an increase in SAR with delta F being the bandwidth of the pulse. Right, so it turns out, as we'll see later, that as you increase the bandwidth of a pulse, if you hold the flip angle and the pulse duration fixed and increase the bandwidth, then that requires an increase in the magnitude of the RF. Okay? Now, just so you know the units and understand some of the parlance of RF pulses, I'll talk about typical RF magnitudes and units. So amplitudes of RF pulses are typically measured in units of Gauss or in microtesla. So the typical max B1 magnitude, RF field magnitude in the body, or in the head, is about 1/4 Gauss, and that is equal to 25 microtesla. So a Gauss is 1/10,000th of a Tesla, and if you convert that, you get 25 microtesla. Now, then 1/8 Gauss is the maximum field that you get usually in the body. It's a little bit smaller because you're using a body coil, and it's sitting further away from the subject. And that is equal to 12.5 microtesla. Okay? The other thing that folks quote this in, especially in NMR, is in units of kilohertz for protons. That is, how fast does the magnetization precess around a constant B1 of a given strength, right? So to see that, we can express B1 in kilohertz as being equal to gamma over 2 pi, the gyromagnetic ratio, which converts field strength to frequency, times B1, which is in units of Gauss, right? And so then gamma here for protons is 4257, sorry, that's a 4, 4257 hertz per Gauss. Okay? And so 1/4 hertz is about 1 kilohertz. And that means that you get a 2 pi rotation in about 1 millisecond. Right? So the period of this guy is 1 over 1000, so that's 1 millisecond. Or a pi rotation in about 0.5 milliseconds, a half a millisecond. Okay, so here's graphically what's going on. You have the RF pointing along this direction, and you're looking at the frequency with which the magnetization processes in the YZ plane. Right? And that, if you have a 1/4 Gauss field, that frequency is about 1 kilohertz. Okay, so that's all. So next time we're going to get into the small tip angle approximation and some one-dimensional pulse designs. Thanks.